All right. Hi, everyone. Let me share my screen. And, oof, that's always that. Where do I share my screen? Share. There you go.
Yeah.
Okay. Hello, everyone. My name is Julio Ortiz, Sustainable Structures Lead at TM Consultants here in New Zealand. And welcome to this webinar hosted by IFC Task Group 6.7, Sustainable Structures to Foster Climate Change Mitigation and Transition Towards Carbon Neutrality. Before we begin, a brief word about IFC. The International Association for Bridge and Structural Engineering is a global scientific and technical association comprising members from over 100 countries and 58 national groups worldwide. Founded in 1929 and headquartered in Zurich, Switzerland, IFC brings together professionals involved in all aspects of structural engineering, from design and construction to maintenance and dismantling, considering not only technical and economical aspects, but also environmental, aesthetics, and social impacts. We are also excited to announce the upcoming IFC Congress taking place in Ghent, Belgium, from August 27th to 29th, 2025. This event is co-organized by the Dutch and Belgian national groups of IFC in collaboration with Ghent University. The early bird registration is now closed, but general registration is open from July 1st to August 15th. For more details, please visit the Congress website. We'd love to see many of you there. We're thrilled to have you with us today as we share our goals, structures, and the path we are taking to support the engineering community in reducing greenhouse gas emissions and promoting sustainability across the full life cycle of civil engineering structures. Our mission is ambitious but necessary, as the built environment accounts for a significant share of global emissions. We, engineers, researchers, and practitioners, have a critical role to play in shaping a climate resilient and low carbon future. Through this task group, we aim to promote strategies for designing low carbon structures, address barriers and highlight opportunities for sustainable construction, advance life cycle assessment tools and methodologies, benchmark environmental footprints, and share best practices and emerging innovations across our global network. Today, we'll walk you through our vision, our planned deliverables, including an upcoming SED book and a future seminar, and most importantly, how you can get involved in this effort. To kick us off, I'm pleased to announce the convener of Task Group 6.7, Dr. Elena Gervasio, professor of the University of Coimbra and chair of the Task Group 6.7, who will give an overview of our mission, scope, and current progress. Elena, the floor is yours.
Thank you very much, Julio. So thank you very much for coming. Good morning, good evening, good night. I don't know, wherever you are. It's very nice to have you all here. So as Julie was kindly introducing, so in fact, our mission today is first to present the task group, what are our goals, what are our ambitions. And then I will talk a little bit about one project that somehow supports some of the things that we would like to do in this task group. So let me share my screen. So I hope you can see my screen. Is it okay? Can you see my screen?
Yeah. Yes.
Just to confirm? Yes? Okay. Okay. So our task group is in fact dealing with sustainable structures to foster climate change mitigation and transition towards carbon neutrality. So what was the main motivation for the creation of this task group? So we know, and probably most of you that are watching today are involved in the construction sector. And in fact, the construction sector has a huge impact on the environment. Of course, we can talk about the extraction of raw materials. So we know that the construction sector accounts for more or less 50% of all raw materials that are taken from Earth. We can talk about the construction and demolition waste that in Europe, for instance, account for 1/3 of all waste that is produced. But one of the major priorities, let's say, currently, due to the climate emergency, is the mitigation of carbon emissions. And in this case, the construction sector is responsible for about 40% of global carbon emissions. So this is in fact a major problem of the construction sector, and we have a huge responsibility upon the achievement of the Paris Agreement goals. So this was in fact the main motivation for the creation of this working group. And although, and we know the amount, let's say, there is already a very big number of initiatives to lower the emissions in the carbon sector, but as we can see here, and this is the global building climate tracker, as we can see here, is that, so if we see in this dashed line, this is our, let's say, zero carbon building stock target in 2050. And what we are observing today is that we are getting further away of this line. So if you see on the right side, so we are currently 9 points behind this line. So compared with 2020, we are getting further away. Okay, this was the pandemic year. So even we forget about this, if we look at 2019, even here we can see that we are getting further away from our track. So it is really important. I mean, the reduction of carbon emission in construction sector still is a huge problem. And of course, as I said, this was one of the motivations for this task group. So our mission, as I said, is to establish somehow a framework for assessing the life cycle greenhouse gas emissions of structures and to foster the transition towards a low carbon built environment. Of course, we will also deal somehow with other relevant emissions because we know, of course, greenhouse gas emissions are very important, especially for the problem that I have just mentioned, but somehow there are some trade-offs between environmental impacts, and that's why we will also to focus or to highlight also some other environmental impacts. This is important also for the construction sector. So we created some topics for discussion among our task group. So for instance, strategies to halt greenhouse gas emissions, focusing, of course, on the design of low carbon structures. And today, we are going to hear about this as well. Of course, to identify main barriers and opportunities towards climate neutrality and sustainable construction, methodologies and tools for the life cycle assessment of construction works, carbon environmental footprint and benchmarking of civil engineering structures. And here I just want to highlight that our goal here in this task group is mainly focused on buildings. And this is because there is already currently another task group working on bridges and other infrastructure. So not to overlap the work of these task groups, we are going to focus mainly on buildings. Of course, new materials, innovative materials, special innovative materials with low embodied carbon. This is also important for our task group. And of course, review of standard and best, let's say, best construction practices for buildings. So these are the main topics. Of course, we are open to other topics. If it is any relevant topic that someone would like to introduce to our task group, of course, you are welcome to do so. So Now I'm going to talk a little bit about what are the active tasks currently. So one of the tasks now is gathering of real case studies featuring buildings with distinct characteristics, let's say characteristic constructions. For instance, buildings that were reduced, thinking about embodied carbon with innovative materials to reduce embodied carbon, or buildings that somehow enhance energy efficiency, buildings close net zero buildings, and so on. So not exactly like this kind of buildings, because these buildings was generated by IA, so it's not really the kind of buildings we are looking. This is just not to introduce some pictures for which I don't have rights to publish. But what I want to say with these pictures, that we are really looking for real buildings, so not AI generated buildings. We are looking for real buildings, but as I said, buildings that somehow differentiate from the conventional construction style. And here I've called, of course, so the type of data that we are looking for is from design offices, from contractors, because we don't want to see only in the production stage or construction stage, let's say, in terms of the type of build of the material that were used, or in terms of design strategies, but we would like also to have examples of construction practices, also in terms of the lifetime of the buildings, for instance, the adaptability of the buildings, refurbishment of buildings, and so on. And of course, if we go to the end of life stage, buildings that can be demountable, that are already being used, and so on. So this is the kind of case studies that I would like. So here I call again for all of you that are watching today, if you are involved, if you are in the design offices, you are working for contractors and so on, and if you have access to such data, and of course you are aiming to share this data with us, so please, you are welcome to join us, or of course to contact us, because we really would like to have this collection of case studies. As Julie was saying in beginning, one of our goals is then to publish one of the IAP's publications with these case studies. So this will be one way also of promoting your work. So please feel free to contact us and to provide us this data. So this is one of the tasks, active tasks. The other task that we are currently developing is the benchmarking of building structures. So here the approach will be the following. So we would like also to collect building data, but in this case, it's general building data. So I'm not focusing only on these special types of buildings, also these buildings that can differentiate from other buildings. So in this case, we are looking for all types of buildings, so conventional buildings, but also good buildings or improved buildings, if you wish. But in this case, what we would like to have is not really the building as a final product. We would like to go into details, and in this case, we would like to go into the bill of materials of the building. And why? Because we would like to produce some benchmarks, and to produce some benchmarks, as you know, so we need a common base for comparison. So we know, and I suppose you are all aware that currently there are already some reference values all around the world for buildings, for the embodied carbon of buildings, for instance. One of the limitations of the existing values is the way they were developed first, because as far as I know, there are already some databases for this kind of data. But as far as I understand, and of course this is will be open then for discussion, what I think one of the limitations of the current databases is that they don't have the same basis for comparison. And what I mean with this is, for instance, in terms of the scope of the analysis that led to that values, the databases that were used, different scopes, as I said, so are many different assumptions that were taken. So I really don't think that these values can be somehow compared. And this is what we want to avoid in this case. So that's why we are asking not for the building, the final result of the building. In this case, of course, our goal is the benchmarking the carbon emissions of buildings. So we are not looking for the final value. We would like to have our own value based, of course, on the bill of materials of such structures. And we are going to focus only on the structural part. So not the entire building, but only the structures. So we are focusing on the embodied carbon of the structure. Of course, I will call also for our help to help us to build this database. Of course, in this case, the building data will be anonymous, so we are not going to share the building, this kind of information for the individual building, so this will be anonymous. Of course, what we can do somehow to compensate the sharing of this data is to provide the information for whoever will provide us the data. So we can provide the processed data, and the processed data will be the LCA of the building. So based on the bill of materials, we are going to perform the LCA, the life cycle analysis of the building, of course, focusing on the greenhouse gas emissions, and we can provide these data to the sources, to the different sources of the building. This is one way somehow to compensate for the effort to provide us and willing to provide us this data. And of course, based then on our own values calculated by us, then we can provide some statistical analysis, and then these results, of course, will be public. So we would like to, in the end, to provide the results that we have for these buildings. After this initial presentation of the task group, I will provide a very brief presentation also of a project that somehow supports the work that I'm explaining here. And then maybe it will be a little bit easier to understand exactly what we want with this task of benchmarking the carbon emission of buildings. So in the end, what we would like to have is this type of reference values all around the world. So not on a specific place, but because we know that there are specificities around the world in terms of seismic area, for instance, in terms of other loading conditions. So of course, it is not possible to have a single value for the entire world, also for the different types of building typologies. So what we would like to have is different types of building typologies and all around the world, so we can have these different reference values for the world. And also, of course, another active task is the review of guidance and recommendations towards a low carbon design of structures and infrastructure. So you are aware for sure that there are many different guidance currently available. And the idea is also to make some collection of these data and review. We will review and discuss some of these guidelines, and this will also be one of the tasks of the missions of our task task group is also to promote this kind of discussion. So over our period, we'll promote some webinars of podcasts with discussions about these different strategies. And then the expected outcome, as already Julio has somehow explained, is first to provide guidance and recommendations. So we'll have a sad book with such guidance and recommendations on the review that we will carry out, and the discussion of the different available documents, and also the set of benchmarks for building searches. So this will be one of the output, and the other output will be the portfolio of the case study. So this is the first task that I mentioned. So in this case, we are going to have this publication, but with real case studies. So that's why I said this is also one way of somehow promoting the work that you are doing. So I think this is also good for you to share the data with us. So again, so please feel free to join us. So of course you can join us directly in our task group. So of course we are aiming to have more members in our task group. So you can either go through the apps website or other, or else you can contact us directly. So either to directly be involved in the task group, or as I said, and because this is really one thing that we need for our task group, if you want to share the data with us, in terms of the real case study buildings, or in terms of specific data for the bill of materials, so that we can carry out our benchmarks. So we really appreciate your contact. So this was the first part. So now I will provide also some brief overview of the project that I was mentioned and that somehow support one of the tasks that I have just referred. And this project was carried out some time ago. It was entitled Performance-Based Approach for Sustainable Design. So this was one of the projects I was involved while I was working for the Joint Research Center. So it's a research lab from the European Commission. And the idea on this project was to measure somehow eco-efficiency. And eco-efficiency can be somehow understood as a relative measure. So we have the performance of, let's say, of structure currently, and we have to understand what we want to achieve. So we need somehow a target, and we can measure the distance from the values that we have and this target goal. So eco-efficient can be understood somehow as a relative measure between these 2 points. And this was the idea behind this project. And if we have these target values, then we can establish somehow some classification for the performance of the building. So this is one way or one example of such classification. So we can have a very high standard building, and then we can further go down. But for this, of course, we need to have very good reference values. So we really need to know where is our target. So the idea in this case was to have a model for sustainable design in which we could compare the performance of our building and compare this performance with a reference value. Okay. So the idea of this is based on a limit state function. So this is the let's say, the philosophy behind the Euro codes for structural design in Europe. So this is the limit state function in our Euro codes. So the idea was also to make the harmonization between structural design and sustainable design. So as I said, the idea behind the Euro codes in Europe is based on this limit state approach. And also in this case, in terms of the sustainable design, the idea was to have a limit state function. So the main reason, as I said, behind the development of this approach was somehow to harmonize structural design with the sustainable design. And in this way, we would empower structural engineers to foster both safety design, but also sustainable design. And these will align with the goals of the design with the environmental goals, such as the embodied carbon. So the idea in this project was really to define this limit state for sustainable design. And the methodology was somehow similar to the one that I have described for the task group. So the first idea was to develop a comprehensive model for LCA. So a model was created so that all buildings were calculated based in the same model. And in this case, of course, a standardized approach was considered because we need a very good LCA model. So in this case, the model was developed according to the European Standards for Sustainable Design, EN 15804 and 15978. And based on this model, then of course, we did a collection of building data, again, focusing on the structure. So as I said, even in our task group, so the idea was to limit the analysis to the structural system of the building. We also focus on residential and office buildings. So we collect data from residential and office buildings. And then based on the data, so the data was collected again based on the quantities of materials for the structures. And then according to the model that we developed, we quantified the benchmarks. So the model was implemented in one of the LCA softwares. In this case was Gabi software. So Gabi now has changed the name. Now it's called LCA for experts, but it's still the Gabi software. So this software is very interesting for those we are familiar with the software because it allows to create a parametric model. And this is one of the models that we can also use in our task group. So this model takes into account the complete life cycle of the building. So it's not only the production stage, according to the European standards. We have a standardized bill of materials. This bill of materials can, of course, be improved, and it will be improved in our task group before sending to the potential contributors to the task group. But it allows to perform the LCA of the building. So here, this kind of tools ensures that we have the same basis for comparison. So the results we have from the models will be based on the same tool, and this ensures that we have the same basis for comparison. Of course, this model also integrates different types of materials. We are not only focused on one type of material. So, and this is also the idea of this webinar today, is to call for persons from all types, involved in all types of construction, so steel construction, concrete, wood construction. So we'd like to have all these types of buildings in our task group. For the model that was developed, and because the model was based on the life cycle approach, and we know that life cycle approach as cannot skip the amount of uncertainties that are involved in terms of the parameters, in terms of the assumptions, scenarios, and model uncertainties. So in the previous project, this was taken into account. So we took into account the different uncertainties in the different types of uncertainties, and based on the probability distributions for most important parameters, the uncertainty analysis was carried out by Monte Carlo simulation. So based on the collection of case studies and on the statistical analysis that was carried out of the different buildings, and the buildings were classified according to the table that you see below. So the focus was residential and office buildings, but then a different classification was done in terms of the type of buildings, in terms of the number of floors, for instance, and then in terms of the type of structures, so whether it was a reinforced concrete structure, a steel structure, the composite structure, and so on. So this was the type of data that we were looking for at the time, and that we are looking for now also as well. And of course, as I said, so it is not possible to have just a single value for the entire world, because there are, of course, differentiation factors. So for instance, climate region is not that much important in terms of the structure itself. That can be an impact factor as well. But of course, we have different seismic regions. So this is just in Europe, for instance, but around the world, we have also this. So, and of course, the structure is very much dependent on this. So we cannot compare a structure that is, of course, designed for a building with a high risk in terms of seismic with a low risk. So of course, we have to take into account also these differences, and also in terms of all the other vulnerable regions, for instance, in terms of climate change. Now we are expecting also to change. Even the Euro codes now are already taking this into account, and of course, we have also to consider this. But this in the approach can be somehow considered as an actional annex. So in terms of the Eurocodes for structural design, we take already into account differentiation factors. So there, each member's country in Europe has their own national annexes in which specific aspects are considered. So the same can be considered also for the sustainability limit state. So this was the result that we got at the time. So this is for residential buildings. So here in these graphs, you have the values according to the different modules from the European standards. So for those who are not familiar with these standards, so the different stages of the building, from the production of materials to the end of life stages, are allocated into modules. So as you see on the right side, you have, for instance, modules A1 to A3, which is the production stage. And then you have the different modules. So A4, A5 is the process stage. B, the modules B are for the use stage. Module C1 to C4 is for the end of life stage. And module D, which allocates the benefits and burdens due to recycling and reuse of the structure. So we took into account the complete life cycle of the buildings. That's why we were able to calculate the different values for different stages. So in this case, we have on the upper part, we have the global warming potential, so the carbon emissions, the greenhouse gas emissions, and below we have the primary energy for each module. And of course, the main values or the main difference were for the production stage and the end of life stage. So these were the values that were obtained for the global warming potential and primary energy, focusing on the production stage and on the complete life cycle of the building, so modules A1 to D. But of course, we carried out the LCA not only in the deterministic way, but considering also all the different uncertainties. And the uncertainty propagation was carried out, as I have just explained, by Monte Carlo simulations. And then we got to the final distribution of the global warming potential values for the structure. So we are focused only on we were focused at that time only on the structure of the building. And we did the same for office buildings. So again, we collect all the data. We carried out the LCA of the office building, so we have values for all the different modules over the life cycle of office buildings. And again, we carried out the statistic analysis, but we also took into account the uncertainties on the buildings, and then we got into the final values. Of course, there were some limitations in the previous approach, and the main limitation was to develop this resistant function, let's say. The resistant function here, this is just in comparison with the structural design. So the resistant function here in the sustainable design is our target value. So how can we define this? So in the previous project, as I said, we collect building data, but I have to say that the amount of buildings was not enough. So the statistic analysis was limited because the sample of buildings, let's say, that we have at that time was not really representative of Europe, because we were focusing mainly on Europe at that time. But of course, the time constraint was also a problem because the project took only 2 years. And the amount of buildings, of course, was not representative of the entire Europe. So this was one of the main limitations of the project. There were already some recent developments, and this was done already in the University of Coimbra. So currently, we were having some, let's say, new developments to the previous project. So currently, for instance, for a special type of structure, so this is industrial buildings. So we have a very huge sample of such buildings. So we did the design of many types of buildings, also to the use of generic algorithms. So we create a very huge database of such buildings. So it was able to complete, let's say, to have a more comprehensive database of such buildings. So we were able also to calculate the global warming potential of such building. And then we have like this resistant function for industrial buildings, but in this case, it's mainly steel buildings. And based on this curve, then we can also establish, so once we have these target values, we can somehow classify the buildings or establish some classes for the buildings, as I said in the beginning. So once we have the target value, so now we can see where we want to be, whether in class A or A plus plus, or just go to the mean value. So in this case, of course, one big difference between the structural limit states and the design limit states. So in this case, we don't have collapse of the building, of course, but we really want to be sure that our building has a very good performance. And in this case, with these kind of resistant functions, we can understand how can we reduce the embodied carbon of our buildings. So this was, let's say, this project was somehow or will somehow support the approach that I was explaining, and this is one of the active tasks in our group. So you have, if you are interested, this is some publications that were done in the previous project, and they are available online. So before saying goodbye, so not goodbye, just previous goodbye. So I really appreciate your participation in this webinar today. And of course, I want to call again for your participation, active participation in our task group, collaborating with us in our group, or if you are really want to share the data, so please feel free to contact us directly or through e-apps. So thank you very much. Julie, I'll give the word back to you.
Thanks, Helena. I think for time, we're going to pass directly to Kawa at this point.
Yes. Thank you.
Thanks.
Can you see my screen?
Yes.
Yes, Kawa.
Cool. Hi, everyone. My name is Kawa Andisha. I'm General Manager of Department of Structural Systems at HERA, Heavy Engineering Research Association. And today I'm going to briefly talk about some key results in our circular low carbon building design, which led by HERA and co-funded by Heavy Engineering Research Levy and Building Research Levy Brands New Zealand. I would like to start with fundamental definitions. The first, sustainability. Reminding sustainability has three pillars: environmental, social, and economic impact. Environmental impact has many key environmental indicators, including but not limited to carbon, water use, biodiversity, construction and demolishing waste, and contamination. In this presentation, we will only focus on carbon. Building and construction, as you know, and mentioned previously in the previous presentation, contributes approximately 37% of the global carbon emission. When we talk about life cycle carbon, it has two parts: operational carbon emission and embodied carbon emission. Embodied, according to UN Environmental Program and Global ABC, operational carbon approximately responsible for 75% of the whole building sector carbon emission, and embodied carbon will contribute remaining 25%. Operational carbon is associated with B6 energy usage and B7 water usage, and embodied carbon is associated with the all other modules in the life cycle. To reduce carbon, ICCP Special Report and World Green Building Council identified several immediate actions to reduce carbon. In this presentation, I will just focus on the last two actions: designers specifying low carbon products and design solutions, and building design to maximize reuse, refurbishment, and deconstruction. So let's talk about circular low carbon building design in more details. In a nutshell and just briefly, to design low carbon building design, we introduced a flowchart that you can see in the left side of this slide. So there are some key steps that you need to follow to design circular low carbon buildings. The first one is a building design. The main thing regarding the building design is what design step you need to choose strategies and solutions to reduce carbon. According to global feedback from industry, including New Zealand, the best optimum step to implement strategies and solutions is concept design, around concept design before prelim design. One of the key reasons for this one is that at the project initiation, the ability to influence carbon is high, and the cost related to implementing solutions is low. But when project progresses, ability to influence carbon will reduce and cost associated with implementing solutions will be increased. So that's why that the optimum design, the optimum stage design is really important. The second key step, which is very important, is selecting appropriate strategies and solutions. In our research program, one of the key deliverables was development of a comprehensive unified hierarchy, including all strategies for existing and new building. Built on existing hierarchies in the literature like LETI and ISTRACT E, these novel hierarchy, all strategies here can be categorized into 4 groups. The first group, 4D strategies for new building circular design, design for longevity, design for adaptability, design for disassembly, and design with circular materials. The second group, 4R strategies for existing buildings, building reuse through retention or refurbishment, adaptive reuse of the building through repurposing, disassemble, reclaim, and reuse in new buildings, and demolish, recycle, and rebuild. Even if you need to demolish a building, an existing building, this strategy will encourage you to consider partial demolishing rather than the whole building demolishing. The third group is 2L, 2 low carbon strategies, which is applicable to both existing buildings and new building. And the fourth strategy, which is a novel one, and is is the first time that this strategy has been considered and added to a hierarchy, is construction 4.0. So construction 4.0 is a new generation of construction which utilizing Industry 4.0 technology and will deliver several low carbon circular design strategies that can reduce carbon and can reduce the environmental impact of the building. But Construction 4.0 has a hybrid role with, like any other strategies, it encompasses many solutions, but also can bridge existing buildings to new building by utilizing novel technologies like, for example, digital twin, 3D scanning, drone. Construction 4.0 can contribute to development of the construction guidance, which currently is one of the most critical gaps in the context of sustainable building design. And the existing buildings can be deconstructed rather than being demolished. So if we can successfully deconstruct existing buildings, their materials can be used in future new buildings. So each strategy encompasses several buildings. It was our intention in proposing the solutions was ensuring that they are readily available and it's possible to implement it in New Zealand and globally. So if you are interested, you can refer to one of our reports. Here are R4164, Low Carbon Circular Design Guidance Framework, which if you refer to our website, it is free to everyone. You can download it and read these documents for more information. The third step in circular low carbon building design is life cycle assessment, which is a key part. And it is very important when you do life cycle assessment, you need to consider the whole life cycle. Considering a part of life cycle like A1 to A3 or A1 to A5 will just provide misleading information, doesn't provide a comprehensive information. So to be able to really do a comprehensive analysis and reliable results, you need to consider the whole life cycle. However, implementing circular low carbon building design may provide some complexities. One complexity is about, in previous slides, we talk about the various environmental key indicators. When you, we all agree that carbon reduction is important, and carbon is a very important key environmental indicator, but carbon is not the only important environmental indicator. What about construction and demolishing waste is very, very important. What about biodiversity? So by adding them, we increase complexity. For example, if you look at the figure here in a right-hand side, regardless of what strategies and solutions you implemented to reduce carbon, that may lead to increase or decrease the construction and demolishing waste. And if you consider the other key environmental indicators, that complexity will be even more important. Another type of complexity or source of complexity can be due to tension between circular and low carbon design. Any circular solutions will provide lower carbon solution, but low carbon strategies may not lead to circular solutions. And then the example is when you replace a circular building element by a low carbon, which is not a circular element. there is another source of complexity which arises when you replace the materials and building and structural systems. So when designers replace the building and structural systems, they may significantly impact the building performance, the structural performance, like seismic performance, fire performance, acoustic and durability performance. So the comparison wouldn't be apple-to-apple comparison. So it is important, to acknowledge the complexity. And if there is a complex situation, then you may need more tools and further and advanced analysis to be able to inform decision making, like multi-criteria decision making. The last step in a flowchart is comparing the results with the target. If results meet the requirements, then the process is completed. Otherwise, you need some iteration. You need to back to selecting or refining selection of strategies and solutions, and repeat that steps until results meet requirements. So now I would like to go through the case studies and share some key results in our project. The case study is a real building in New Zealand, located in South Island in Christchurch, built in 2013 after Canterbury earthquakes. It's an office building, 3-story. Lateral resisting systems is a reinforced concrete shear wall and one direction, and the other direction is moment resisting steel frame. And flooring system is steel concrete composite flooring system. So as discussed before, all strategies and solutions to reduce carbon can be categorized into two groups. One group, which is complex group, you can't compare the scenarios because they are not apple-to-apple comparison. You need further tools and advanced analysis to inform decision making. But fortunately, there are a group of solutions and strategies that they are uncomplicated solutions. And with uncomplicated solutions, you can reduce carbon, and you don't need to do any further analysis. It is just straightforward. So here, for superstructure, for the building case study superstructure, I have listed a list of uncomplicated solutions, including reversible connections in flooring system, specify low carbon concrete, structural steel, and reinforcing bars. And you can see that that solutions can reduce the whole superstructure carbon by 5%, 8%, 21%, and 17% respectively, which cumulative carbon reduction is 51%. So by utilizing these uncomplicated solutions, it's possible to reduce carbon by 51%. The first solution, reversible connection in flooring system, is just replacing welded shear studs by high strength bolt. And we have the full details and provisions in ASNZS 2327, New Zealand, Australia composite standard, which I'm sure that you have the same we have the same in the other global standards like Eurocode as well. The other solutions in specifying low carbon materials by specifying 40% carbon, and also utilizing Hyundai structural steel, which you can see the comparison of the EPDs for low carbon and high carbon structural systems, and also using the net steel reinforcing bars, which all available. You can reduce emission carbon by 8% for carbon, 21% for structural steel, and 17% for reinforcing bar. So let's move on substructure. The substructure, the foundation of this building case study is a raft foundation. Interestingly, the embodied carbon, the whole carbon emission of the substructure is almost equivalent to the whole superstructure's carbon. It is 95%, almost same as superstructure. These emphasizes that it's important to consider the carbon of substructure. So again, by utilizing uncomplicated solutions, using low carbon concrete and low carbon reinforcement, in this case study, it's possible to reduce carbon emission by 62%. So you remember that we showed at the beginning that operational carbon is very important, and globally, operational carbon is responsible for 75% of the building sector carbon emission. So we in this research, we implemented two solutions. Again, uncomplicated solutions, because we haven't changed any material. We haven't changed the structural systems. We just implemented a regulation, which is about increasing the building insulation. In New Zealand, we called 2023 H1, and also installing thermal bricks, which is a global practice everywhere to install thermal bricks. So if the building case study used boiler and air conditioning, then these insulation regulation 2023 H1 and also installing thermal brick both can reduce carbon by around 60%. However, if the building use heat pump, which is common in New Zealand and Australia, then installing thermal brick can contribute to 30%, can lead to 30% carbon reduction, but increasing insulation will not affect significantly the carbon emission, the operational carbon emission of the building. So this brings me to closing remark. I would like to advocate for sustainability, and I will remind everyone that sustainability has three pillars: environmental, social, and economic. A transition from low carbon to sustainable design is essential, which is one of our targets in this task group. A low carbon solution is not always a sustainable solution. An example is when you replace a structural system by a low carbon structural system, which will negatively impact the other key environmental indicators and is more expensive system. That alternative is not sustainable solution, is a low carbon solution, and we should understand the differences, the key differences between low carbon and sustainable solution. We may go to lower carbon, but we may negatively impact environment and economic and social as well. Optimization is important. In design, in building design, it's very important to be efficient, not conservative. Conservative design will impact the carbon significantly. Engineers, especially since we talk about superstructure and substructure, structural engineers need to understand their critical role in influencing the whole life carbon of the building. They need to be efficient and precise, and also they need to equip themselves with new knowledge and tools, etc. They need to stay updated with knowledge, tools, and skills. When we talk about carbon reduction, all strategies and solutions can be categorized into two groups. Group one is uncomplicated solutions, readily available, can significantly reduce carbon. You could see in a case study that it was possible to reduce more than 50%. And the second group is the complex solutions. If you use the complex solutions, then you need further tools like and also advanced analysis and further tools like multi-criteria decision making to be able to inform decision making. Otherwise, they will not be apple-to-apple comparison. In closing, I would invite everyone to check the task group 6.7 website and also HERA website. We have several guidance and tools that can help you with reducing environmental impact and develop more sustainable built environments. Thank you. And I would like to acknowledge funding and also whole people who contributed in this research. Thank you.
Thanks, Kawa. Thank you for your presentation, Elena. And Kawa, the presentation was really clear and inspiring. It's good to see that we are building a good structure within the task group, right? And that we're progressing in order to achieve low carbon design and a more sustainable design. So just to acknowledge the time, we have more time if the participants want to stay, but to progress and maybe comment a little bit, have a little bit of question to start with, that is basically considering the low carbon strategies that we have available already, right? Like Kawa mentioned it very well. Then what do you think is stopping us from making these strategies like standard today? What is stopping this to make it a standard practice? Basically, that's the question. I don't know if you want to start, Elena.
Yes, Julie, thank you. Of course, I mean, the problem is, as I saw and as I showed in the beginning, is that we have all these initiatives all the while to reduce carbon emissions. We have already some very good examples, of course, but we are still not in the path. So really there is something that is some kind of a barrier that is really not, we are not able still to overpass. And I believe that one of the things is sustainability. Everybody talks about it, but the thing is, I think it's something that especially engineers, or I will say all professions in the construction sector, look at sustainability as something that is good to have, like kind of a label, but not something that is included in the design as we have all the safety criteria that we have to consider. So I think one of the things is really to empower civil engineers to have tools, to have methodologies that can be integrated into the design. I would say that, for instance, in Europe, the Eurocodes were reviewed recently, and it was a missed opportunity because Eurocodes still don't address sustainability directly. And I think this is a missed opportunity because it was really a chance to provide civil engineers also with the criteria that could be helpful for the design of the buildings. And this is also somehow become mandatory because we have the revision of the construction power regulation, which demands also for sustainability. So things are not, I mean, they are not really aligned, I think. And the other thing is, and I can talk by myself because I'm a professor in the University of Coimbra, and this is something that we try to provide to new engineers, structural engineers, is also to highlight, I mean, to provide them the basis to consider to perform the sustainable design, for instance, life cycle approaches. So we are trying to call their attention from the very beginning, so that when they get into the professional sector, they are already aware and they have tools already that they can consider for the design. But I think we really have to align structural design with the sustainable design. It's not just a label. It's not something that we can have some consultative dealing with that, and then in the end we have a very good label. It's something that we really have to consider from the very beginning, because as Kawa was saying, it is very important to consider sustainability from the very beginning of the design process. It's not something that we can add later on. So maybe
Yeah,
Kawa
absolutely.
even
It comes from
count.
concept design, right? So
Yes.
try to summarize it, this has to do with information first and legislation also, right?
Yes. Yeah.
Is anything you would like to add, Kawa?
Yeah, I totally agree with what Helena said. I just would like to mention that in process of revision of steel standards, New Zealand steel standards, which I am a member of committee. Fortunately, we were able to propose some changes to facilitate sustainability, which was great. But I think if I back to the barriers, I think one of the barriers is probably lack of data, which is one of the key objectives of this task group as well. So without sufficient data, it is very, very difficult to to develop a standard. Even when we talk about the results, I think we are talking about the results for a case study. We are not talking about a very generic one. You know what I mean? So whatever we show, maybe for another case study would be less or more or less. So data is a key part of the things. Another thing is, I think regulations and regulatory framework in each country can actually influence standardization a lot. So if if we need to understand the barriers, the regulation barriers, or incentives from regulators, which can change the standardization.
For sure. I mean, it seems like we, at the moment, it depends on the country that you're in, is how the legislation helps or doesn't help to progress with sustainable design, right? Following onto the same kind of line, what do you think about the cost? Does it cost more to do a sustainable design or not really?
It really depends on the solutions that you select. I believe if again, if we select any solution that is more expensive than existing solution, then that solution is off track sustainability, because sustainable solution shouldn't be more expensive. In a case study that I showed you, all solutions that I showed are completely cost neutral. There is no cost increase associated with implementing them. Regarding the carbon and the superstructure, that we did some analysis, and replacing high strength bolts by welded shear stud is pretty cost neutral. Implementing low carbon materials in superstructure and substructure, there is no cost associated in New Zealand, which I believe it would be the case for many other places. Regarding the operational carbon, yes, when you address the thermal bridges, you may add some initial cost, but when you consider the reduction in the cost, the upfront cost is really negligible, but you will save a lot during the building operational stage. So, all solutions I provided in the case study are sustainable because they don't, they reduce carbon, they increase circularities of the buildings, reusability of the buildings. They don't increase the cost, and they will not affect other environmental key indicators compared to the reference building. That's why that they compared to the reference building, they are sustainable solutions.
Absolutely. And it seems like, well, Elena, you said the same, right? Like in terms of...
No, exactly. I was just complementing what Kawa was saying, because when we talk about sustainability, of course, we are talking always about the life cycle perspective. So we have to think not only in the present, but what is going to happen with the building over the complete life cycle. And I would say that probably there are cases, and I'm aware of some cases, that probably the initial cost is somehow higher, because if we are thinking about innovative materials, if we are thinking about production of renewable energy, so of course these equipment are not very cheap. So probably the initial cost may be somehow higher, but if you take into account the complete life cycle of the building, then we can have the benefits, then we can see the benefits. So that's why one of and back to the first question, but this is one thing that for engineers, sustainability is somehow a new perspective, because somehow we were, I would say, I will talk about myself. I mean, when I did the course on civil engineering, we were mainly focused on the present. And sustainability is a new perspective. So, of course, this is a challenge for civil engineers, because we are only focusing on what is happening now, but we have to take into account this long-time perspective.
Yeah, especially I think when we don't have that, sometimes we feel that we don't have the power to influence that kind of decisions, right? Like in terms of how everybody's going to live in that building or how it's going to operate, because usually, and especially in this case, we're responsible of the structures. But I think we have the opportunity to raise our hand and say, look, we want to achieve this. So I'm going to go to the Q&A that we have some of the people that have asked. And I think we kind of already answered this question from Kasperi, that he says he or she, I don't know, not exactly a question, but it could be extremely useful to show the differences in the desired service life of the buildings in the results. How is the use phase, modules B, considering this work? I think we've kind of covered it already.
But it's an interesting question, Julie, because I forgot to mention when I was showing that project that I was involved, and it somehow supports what we want to do. The use stage, of course, is very important, especially the lifetime of the building, because one thing is to build one building for 20 years, and another thing is to have it for 100 years. And for instance, design for adaptability and flexibility, this is one strategy to extend the service life of the building. So one way somehow that we address this problem in the previous approach was to have the reference value, for instance, in terms of carbon emissions, divided by the area of the building, of course, by the use area of the building, but also per year. So, the design was made for 50 years. So, of course, these values are divided for 50 years. But if we ensure that somehow the building is able to cope, for instance, with new functional requirements and so on. So if we are able to extend the service life of the building, so if the building is justified to be there for, let's say, 100 years, then this value can be reduced. And this is somehow a way of considering this design life of the building.
Perfect. Sounds great. I'm going to go to the other questions from Peter Dan. Is the team looking at road and rail infrastructure, structured assets such as bridges, retaining walls, and tunnels? I think, Elena, you mentioned something about that.
Yeah. Well, mainly when we first created the group, and the idea was really to focus on all types of structures, but because there is another task group dealing with infrastructures, I'm not sure whether they are looking for this data. Maybe it's one option will be to contact them. Otherwise, of course, if you want to contact us, and of course we can make this contact, that would be great. Otherwise, just contact us or contact them directly, and we'll see, because all types of structures are important for us. We just want to overlap the work between the different tasks group, but please feel free to contact us or contact them directly. I think in task group, 6.6, I believe, the one dealing with the infrastructures.
Yeah, because that's an interesting opportunities. Probably in the
Yes.
future we'll be able to communicate with them and even present together, right? You never know.
Yes,
So
yes, that
thanks,
is planned,
thanks
yes. Yeah.
yeah. And one last
I
question
can
from a
I can
mysterious. Sorry,
sorry. I
just
just
go.
wanted to add to both questions actually.
Ah,
For the first question, I would like to say that this is a very good comment and very aligned when we talk about the whole life cycle analysis, which is very important. If we don't consider the building lifetime and service life, then we miss the opportunity to see the majority of the carbon emission, and it's very important one. So definitely this is very important, which is well aligned with what we way that we looking sustainable building design. Regarding the second one, I believe majority of what we develop will be applicable to bridges and infrastructure.
Yes,
because
yeah, for sure.
For example, the hierarchy that we showed is definitely is applicable to all structures. So while we may in terms of case study, we may our case study is limited to the buildings, but I believe what we will develop will be applicable to other structures.
Yeah, for sure.
yeah, it sounds like at the end we're providing a set of tools, right, for our toolbox.
Yeah.
So no matter where you're designing a steel structure, a steel building or a steel bridge, it will be similar, right? There will be
Yeah.
things that you can take from one to another. And last question that I have from a mysterious attendee who wants to stay anonymous. It says it's all very well to call low carbon steel, for example, a Hyundai, but access to these materials is limited, as we know. There is not enough steel in the world to allow these construction options. What do you think, or how we can, develop these things? Because it's quite important to understand
Sure.
how we're
Sure.
doing this.
Yeah, of course. One of the things that I also refer is, of course, we are not focusing on just one material. It is the case that in case of Kava and myself, we are mainly dealing with research focusing on steel structures. But the idea in this task group, and we have already members in our task group that are coming from other industries, from concrete industry, mainly concrete industry, but also from others. And this is why it is important today, our webinar, and to call for other members dealing with other materials, because of course it's not only steel that is able to cope with low carbon structures. Other materials, other industries, concrete industry, for instance, they are making very big efforts to have low carbon concrete. Wood, we have already the idea of wood, the biogenic carbon that can be discussed, of course, but it's also an important material. We cannot forget about other materials. So it's not only the question of steel. We are looking for all kinds of materials because we believe that all kinds of materials can contribute to a low carbon environment.
Yeah, I would say that this is an interesting comment, which is I believe is if we want to build all our buildings with low carbon steel, then easily we don't have enough stock, right? This is same for concrete. This is same for timber. We don't have a stock to use those materials for all our to use low carbon materials, including timber, steel low carbon, and concrete low carbon for all our buildings. That's true, but that will not stop us to use them, because they will deliver they will lower down. I would like to specifically mention New Zealand situation. In New Zealand, we have a New Zealand steel, which they will produce reinforcing bars and plates. So all plates using in our buildings in New Zealand, including welded beams and welded columns, all produced by New Zealand steel. We don't have any imported. Mainly are New Zealand steel. So They are at the moment building an electric arc furnace, which will be operational by the end of this year, and they will have two products. One would be the embodied carbon would be over 50% reduction to current products embodied carbon. The other one would be over 85% reduction carbon. So you can see that while globally speaking, I agree with the limited material globally, but in New Zealand, for example, for reinforcement and plates, we don't have any limitation. They will cover the whole New Zealand construction sector, and without problem, they will completely, ensure that we have that low carbon material for all buildings and infrastructure in New Zealand.
Yeah, I believe that just to add a couple of things there, as you said correctly, it definitely is country dependent, right? Depending on the region that you are and what you have as resources, right? The energy sourcing, for example, plays a huge role on construction, right? And the other one that I want to say also, I believe as structural engineers, we are taught to design efficient structures, and efficient design is sustainable design, right? So it's not that we want to use all the timber in the world just to put timber everywhere and then we have a sustainable building because we're taking all the trees from the world, right? But if we keep on this effort of, informing people, teaching what are the alternatives, and as Kawa greatly showed on his example, how some options that you already have at hand can reduce a lot of the carbon that you are actually designing for, and that will mean that people building that building will reduce the carbon output, then we can do this. And that's, I think, the whole point. As engineers, we have a key role to play in all of this search and aim to have low carbon buildings.
Yes.
So I think from this point, well, we've been over the time for almost 20 minutes, which I think is just because we're very interested in this type of topic. I hope that all our attendees had a great time. And again, if you have any questions, if you want to contact us, Brenda already put all our contact details on the chat. So feel free to contact us, reach out. If you want to be part of this task group, please contact us again. And definitely we will have many webinars or other kind of documents. We will be producing them, so you will be having access to all of them. So without anything else to say, unless you want to say anything else, Elena, Kawa?
And now I just want to thank you everyone to be today. Just again to reinforce what you had just said. So if you are interested in any of the topics addressed in this task group, please contact us. You are very welcome to join us in this task group. And of course, if you have access to the data that we have described and you would like to share, please contact us. So this is it. And thank you very much for being here today with us. Thank you, Julie, also. And Kawa.
Thank you, everyone. Thanks for participating in this webinar. And yeah, it was great to see everyone. Yeah.
Thanks, everyone. Thanks for joining us, and we'll see you next time.